Hello, I'm Nilam Tathawadekar. Today I'll be presenting my work on modeling of the nonlinear flame response of a Bunsen type flame via multilayer perceptron. This work is done in collaboration with my colleagues at Technical University of Munich. Over the last decades, the emission regulations for aircraft engines have been steadily tightened. To meet these regulations, lean premix combustion systems are developed. In gas turbines, this development is hindered by the risk of thermoacoustic instability, which causes undesired vibration that may severely damage the engine. Perturbations in incoming flow causes heat release rate oscillation, which in turn causes acoustic oscillation. The positive feedback loop between acoustic waves and unsteady combustion gives rise to thermoacoustic oscillations. These thermoacoustic oscillations often surface as late as the engine has been built and tested. Hence, it is beneficial to predict these instabilities at the design phase. To predict the amplitude of these acoustic oscillations, low-order methods have proven to be useful if combined with appropriate models for the nonlinear flame response. This work focuses on using a neural network model to obtain this nonlinear flame response. A well-established strategy to model such a nonlinear flame response is by means of the so-called flame describing function. It characterizes the fluctuations of heat release rate Q dot prime produced as a response to the upstream velocity perturbations U prime, which are characterized by a well-defined frequency omega and amplitude U prime as shown here. Conventionally, to obtain this FTF, the inlet velocity of CFD simulation is excited harmonically. Both the frequency and amplitude of the harmonic are varied. An analytical fit is obtained to model the flame response. Although useful, the FTF approach is restrictive as it assumes that the flame responds exclusively at the same frequency as the input signal U prime. FTF neglects the possible apparition of harmonics in the response Q dot prime. To extend this FTF framework, Heringer et al. Proposed an extended FTF called XFTF. It includes additional transfer functions relating higher harmonics of the heat release rate to the forcing velocity. As shown earlier, FDF is coupled with an acoustic network model to obtain the amplitudes of thermoacoustic oscillations. A more reliable yet more complex alternative to the FDF acoustic network approach is the hybrid CFD low-order model. It consists in coupling CFD, which models the flame response, with an acoustic solver. This method predicts limit cycle amplitudes accurately. Unlike FTF, it captures the nonlinear interaction between fundamental frequency and associated harmonics to predict the self-excited oscillations. But all these approaches require multiple CFD simulation to obtain the limit cycle predictions. So, what can be done to reduce this computational cost? We need methodology where the flame models can be obtained by a single CFD simulation, where a carefully designed input signal U prime is applied during a short physical time window. Polifke proposed a method where broadband excitation signal is applied to CFD and combined with system identification to capture a linear flame response called a flame transfer function in one shot. The present work uses the data collected by the broadband forcing and makes use of a machine learning based approach to model the nonlinear acoustic response of flames. We will look at the case of Cornelius flame, then discuss the details of a neural network model called multilayer perceptron. In the end, we will discuss the results obtained. Left-hand side figure shows the experimental setup of the Cornelius flame. It's a lamina multi-slit burner of a premixed methane and air mixture with an equivalence ratio of 0.8. Right-hand side figure shows the 2D CFD domain with symmetric boundary conditions. Here I show the response of a flame for a monofrequent excitation. Following the work of Yench et al., we formulate a regression problem which is solved using a neural network model. The objective for the neural network is to find a mapping F such that heat release rate fluctuation at time t depends not only on the inlet velocity fluctuation at time t but also on some history of it. This reflects the time lag nature of the system. To solve this problem, a multi-layer perceptron is used. Let's look at its architecture in the next slide. This figure shows the typical representation of a multi-layer perceptron. Tan H is used as an activation function. Compared to the work of Yench et al., dropout is used as a regularizer to avoid overfitting. More deeper and wider networks are used to model the flame response. Mean squared error is used as a loss function. The best performing neural network model obtained for a given data had 128 neurons in the first hidden layer, 64 neurons in the second hidden layer, and 32 neurons in the last hidden layer. Let's look at how MLP is trained by using given input-output data. 70% of the input broadband excitation signal is used as a training set and 30% as test set. 20% of the training set is further split into validation set. Training and validation set is used to train different MLP models with different hyperparameter settings. The predicted heat release rate is used to compute the mean squared error on validation set. The mean squared error fit with CFD data is calculated on the validation data, which is not used during the training. Model with the lowest validation set error is chosen for further processing. This figure shows the comparison of actual and predicted heat release rate by best MLP model for test data. MLP model predicts the time series response accurately. This measure is crucial as it determines the choice of neural network architecture and hyperparameters that is selected for further tests. The multi-layer perceptron is trained using broadband excitation signal. To obtain the flame response, the best performing MLP is used to predict the response of monofrequent inlet velocity. Recovering the FDF is not obvious given that the input signal to obtain the FDF, that is harmonic excitation, is nothing like the training data, that is broadband excitation signal. So the neural network needs to learn both the frequency and amplitude response from a single training data. To assess the performance of trained MLP, the FDF is obtained from it and compared to the CFD results. To do so, the best performing MLP model is excited with monofrequent excitations of different amplitudes. Frequencies from 50 to 500 Hz and amplitude levels of 0.5, 1.0 and 1.5 are considered. Figure on the right hand shows the results obtained. Straight line indicates the prediction by neural network model and markers indicate the CFD results. Different colors indicate the different amplitude levels used. The shaded region in the figure shows the bound of prediction using the estimates of 5 best performing MLPs. Tight bounds are achieved, which indicates less uncertainty around the prediction. MLP recovers the gain and phase response of the flame satisfactorily. As discussed in the introduction, the FDF neglects the excitation of higher harmonics. The ability of neural network to predict the higher harmonics is assessed here. The trained neural network model is excited with 3 different sinusoidal signals, each with frequency of 100 Hz and amplitudes of 0.05, 0.1 and 0.5, and the results are compared with the equivalent excited CFD simulation. This figure shows the FFT contents of the heat release rate fluctuations at the fundamental frequency and its higher harmonics. At 0.05, the output is purely sinusoidal. For amplitudes of 0.1 and 0.5, higher harmonics start to appear, which is a trend that the neural network also predicts. This behavior is consistent across all other frequencies. This shows that the proposed neural network approach is capable of learning more complex interactions between harmonics than the FDF. We will now assess whether neural network can accurately predict self-excited oscillations. To do this, trained neural network model is integrated into an acoustic network model through flow velocity fluctuations and heat release rate fluctuations. The overall network represents a flame in a duct. To study the stability of the system, the length of the plenum duct is varied from 50 mm to 1000 mm. The amplitudes of the velocity fluctuations are collected. The results of the coupled neural network and acoustic network models are compared with the hybrid CFD low order model by Yench et al. In their work, the flame response was obtained using CFD, whereas in our work, flame response is obtained using trained MLP model. This figure shows the RMS value of the flow velocity fluctuations measured at the upstream side of the burner plate and the dominant frequency of the self-excited oscillations for different plenum lengths. It is observed that the system becomes unstable at plenum length of 160 mm, which is in agreement with the CFD result. Additionally, the neural network model shows a good agreement with the CFD results with a slight over-predictions for higher plenum lengths. Furthermore, the neural network model also exhibits the same trend as the CFD, where initially the second harmonic is dominant, and as the plenum length increases, the fundamental frequency becomes dominant. Finally, the shape and frequency responses of the obtained self-excited oscillations for two different plenum lengths, 200 mm and 500 mm, are shown in these two images. The snapshots of the time series are taken once the steady limit cycle state is reached. An excellent agreement is observed between the neural network based approach and the CFD for both plenum lengths, with the appropriate frequency being dominant in the response signals. This shows that the neural network based approach can provide additional information compared to the FTF method, as it also produces harmonics in its response. In conclusion, multi-layer perceptrons with different number of hidden layers and variable neurons were explored to model the nonlinear flame response of a Bunsen time flame. The neural network model showcased the ability to learn the FTF for the laminar premix flame under study. It uses only one CFD simulation to train the neural network model. The trained neural network model captures the flame response not only at the input frequency but also at higher harmonics. When coupled with an acoustic solver, the trained neural network could accurately reproduce the bifurcation diagram and the limit cycle amplitudes, shape, and frequency contents when compared to the hybrid CFD acoustic solver of Yench et al. Thank you for your attention. Feel free to contact me if you are interested in my research.